For the first time, carbon dioxide and carbon monoxide ices have been observed on trans-Neptunian objects, TNOs, in the far reaches of our solar system. A research team led by planetary scientists Mário Nascimento and Noemí Pinilla-Alonso from the Florida Space Institute at the University of Central Florida, FSI, used the James Webb Space Telescope's, JWST, infrared spectral capabilities to analyze the findings. They examined the chemical composition of 59 trans-Neptunian objects and Centaurs. The pioneering study, published in Nature Astronomy, suggests that carbon dioxide ice was abundant in the cold outer regions of the protoplanetary disk, a vast rotating disk of gas and dust from which the solar system formed. Since it is also widespread among the studied TNOs, more research is needed to understand the origins of carbon monoxide ice. Researchers reported detecting carbon dioxide on 56 of the 59 TNOs observed with the JWST and carbon monoxide on 28 of them, with 6 additional marginal or suspected detections. According to the study, while carbon dioxide is common on the surfaces of the trans-Neptunian population, regardless of dynamic class or body size, carbon monoxide is only detected on objects with high carbon dioxide abundance. The research is part of the UCF-led Trans-Neptunian Object Composition Survey, DISCO TNOs program, one of the JWST programs focusing on analyzing our solar system. Duprat, one of the study's authors, stated, "We observed this region of the spectrum for a large collection of TNOs for the first time, so everything we saw was in some sense exciting and unique. We did not expect to find carbon dioxide so prevalent in the TNO region, and even less so carbon monoxide on so many TNOs. The discovery of these ices could further aid our understanding of how the solar system formed and how celestial bodies may have migrated." Duprat explains, "Trans-Neptunian objects are remnants of the planetary formation process. These findings can place significant constraints on where these bodies formed, how they reached their current region, and how their surfaces have evolved since formation. Being formed farther from the Sun and smaller than planets, they contain pristine information about the original composition of the protoplanetary disk." While carbon monoxide ice was previously observed on Pluto by the New Horizons probe, it wasn't until the JWST, a powerful observatory capable of detecting traces of carbon monoxide ice or carbon dioxide ice on a more extensive TNO population, that this became possible. Carbon dioxide is commonly found on many objects in our solar system, prompting the DISCO team to question whether it existed in larger quantities beyond Neptune. Possible reasons for the earlier non-detection of carbon dioxide ice on TNOs include lower abundance, volatile carbon dioxide being buried under layers of less volatile ices and refractory materials over time, transformation into other molecules through irradiation, and simple observational limitations. Duprat notes that the discovery of carbon dioxide and carbon monoxide on TNOs provides some context while also raising numerous questions. While carbon dioxide likely accreted from the protoplanetary disk, the origins of carbon monoxide are more ambiguous, he says. The latter is a volatile ice even on the cold surfaces of TNOs. We can't dismiss the possibility that carbon monoxide accumulated primordially and somehow survived to the present. However, the data suggests that it could be produced through irradiation from carbon-containing ices. Pinilla-Alonso mentions a widespread theory suggesting the presence of carbon dioxide on TNOs due to the observation of gaseous carbon dioxide on comets. "We observe carbon dioxide as a gas released by the sublimation of ices on the surface or just below the surface of comets," she says. However, since carbon dioxide has never been observed on the surface of TNOs, the common belief was that it was trapped beneath the surface. Our recent findings overturn this notion. We now know that carbon dioxide not only exists on the surface of TNOs, but is also more widespread than previously thought, even more so than water ice, which was considered the most abundant surface material. This discovery significantly alters our understanding of TNO composition and indicates that the processes affecting their surfaces are more complex than we had assumed. Co-authors of the study, Elsa Enault, a doctoral student at the Institut d'Astrophysique Spatiale at Paris-Saclay University, and her advisor Rosario Brunetto, brought a laboratory and chemical perspective to the interpretation of JWST observations. ANO analyzed and compared the absorption bands of carbon dioxide and carbon monoxide across all objects. Despite abundant evidence of ice, she notes a significant diversity in abundance and distribution. While we found carbon dioxide everywhere among TNOs, it is certainly not uniformly distributed, she says. Some objects are poor in carbon dioxide, while others are rich in both carbon dioxide and show signs of carbon monoxide. Some objects exhibit pure carbon dioxide, while others are mixed with other compounds. Associating the characteristics of carbon dioxide with orbital and physical parameters has led us to conclude that carbon dioxide variations likely represent different formation regions and early evolution stages of objects. ANO suggests that while carbon dioxide in the protoplanetary disk is highly probable, the primitive nature of carbon monoxide is less likely. Carbon monoxide can be efficiently produced by continuous ion bombardment from our sun or other sources, she explains. We are currently investigating this hypothesis by comparing observations with ion irradiation experiments that can reproduce freezing and ionization conditions on TNO surfaces. The research has provided some definitive answers to long-standing questions dating back approximately 30 years to the discovery of TNOs, but ANO acknowledges that there is still a long way to go for researchers. Now, new questions arise, she says, particularly regarding the origin and evolution of carbon monoxide. Observations across the entire spectral range are so rich that scientists will undoubtedly be kept busy in the years to come. While the DISCO program observations have brought researchers closer to a conclusion, there is still a long road ahead in analyzing and discussing the results. DePra believes that the fundamental knowledge gained from the study will prove to be a significant contribution to future planetary science and astronomy research. We have only scratched the surface of what these objects are made of and how they came to be, he says. Now we need to understand the relationship between these ices and other compounds on their surfaces, and the interaction between their formation scenarios, dynamic evolution, volatile retention, and irradiation mechanisms throughout the history of the solar system.